Can we just turn the video
This will
off and then
go,
we
yes.
use the slide?
Yeah, we'll turn the video off. So how does one turn the
Stop the video.
stop the video? And then we'll
Let
do
me
this.
show this
Oh
one.
no, that's wrong. It's sorry. There you go. Oh, sorry. There we go. Sorry.
No, it's recording. Okay, so we have the pleasure to have Sergei Gukov here from Caltech. He's known for quantum topology, among many other things, but today he's going to talk about machine learning and mathematical sciences.
Well, thank you very much for inviting me here, and it's a pleasure to visit Columbus for the very first time. So Avidio has been a long-time friend and a collaborator, so thank you, and also thank you for coming to this talk. I have to first give you a disclaimer that I was interested in mathematics for, of course, all my life, but I wasn't interested in machine learning for all my life. I actually was curious maybe 5 years ago when it became fashionable. So I was thinking to myself, well, is it just marketing and newspapers, or can it do something for theory improving and real mathematics, high-level abstract science, which is considered paper and pencil type science? So, well, I guess I convinced myself that it's meaningful. So that's why this talk. Otherwise, I wouldn't be giving this talk. I'll probably give a different one. Yeah, and I hope that in the coming years, mathematics and machine learning will be a field, and we'll be hiring in this areas, just like algebraic geometry and topology are traditional areas. This will become yet another one. At this point, I started building a group in Caltech devoted to this, but my hope is that it will be something bigger and broader. So if you follow the timeline that I'll give throughout the talk, you'll actually see in part why a few years ago there was sort of some qualitative change, a phase transition in this area, and it perhaps will explain why now is a good time to get into this area, or why it may be more meaningful than, say, 5 years ago. So it's happening in real time, and it's very exciting, fast-growing field. So pay attention to the dates. I'm sure you've been staring at the screen while I was giving this introduction, is one of the very early AI systems. So now I'm going back in time really far. So that's one of the first meaningful conversations between computer and a human being in person. And here conversation is limited to a very specific set of axioms in mathematical language. In their world, it was world of basic shapes inside a box, but it's a fairly meaningful conversation. So person is asking a question, how many blocks are not in the box, 4 of them, and so on and so forth. So computer actually basically understands what's going on. So it looks like a conversation that maybe you and I could have. So this first AI system.
If you go back, how old is this?
1971.
What?
1971.
1970. Oh, okay.
So that's the name of the AI system that I just showed you. It was built in 1971 by this gentleman. His name is Sergei Gukov, and he is considered in computer science one of the founding fathers of the subject which is called natural language processing or natural language understanding. So I'll write it on the board. It's usually abbreviated as NLP, that is not natural language processing, or NLU, natural language understanding. I like the second version. They sometimes use it interchangeably because NLP means something else in psychology. So, but in any case, that's a field. And the goal of the field is what you think it is. It's basically understand how we process how cognition works. And for example, he wrote this classic textbook and so on. Back then, he was at MIT. That's where he constructed this simple, or by today's measure, simple AI system that managed to have this sort of conversation. Since then, he moved to Stanford, had lots of successful graduate students. So this is fast forward 20 years. This is 1997. And here's one of his graduate students. So the student in particular, a couple of years later, invented something called PageRank, and you all know his name. His name is Larry Page. So that's natural language processing, natural language understanding, its impact in our world and computer science.
Yeah, if you go back, yes, what is SHRDLU?
Oh, excellent. So yes, I sometimes give as a small homework to figure out what it stands for. Yes, what kind of word is this? So it actually has something to do with some of the first linotype machines. So, but anyway, that's a homework.
Okay.
I had exactly the same question when I saw it first. So. Right, so a little bit more seriously. So what is learning and then what is machine learning? So why is it useful? So in order to understand how it can help us, we have to understand a little bit how it works and how we work. And how we work is also kind of interesting. We learn from nothing. So when we were children, we were basically blank slate. And then how we learn things, we don't have a pre-programmed language in which somebody can explain to us say what a yellow towel is. This is favorite object of my 5-year-old son. So before we can speak or say anything, you have to understand that this is what we call yellow towel. And we basically learn things from experience. We try, make a lot of trial and error. And if things are successful, repeat many enough time, it registers in our brain and it becomes part of well-defined axiom system. And then we expand it and go forward. So Feynman actually described the scientific research process in basic sciences, so I guess physics, but also this applies very well to all natural sciences, including mathematics, is that it's kind of comparable to playing a game of chess, where we see how pieces move on a board, where gods play this game, but we actually don't know the rules, and our job is to figure out what the rules are. And I like this because this is indeed a very good description of scientific process in general, but this is also explains or will help us to understand from this perspective where machines can try to observe the same game of chess on a board and figure out what the rules are or should be. So speaking of game of chess, when I was a kid, I actually happened to know this man. So this is chess grandmaster, Garry Kasparov. And he organized for high school students this chess club, and it was a lot of fun. So I was probably one of the least successful students in that club. But what amazed me even back then, so I was going there a little earlier, this picture is from 92, and I was going there maybe 89 or something, but Gary looked pretty much the same. And what's interesting, computers look pretty much the same. So he encouraged us to play not only against each other and learn various tactics, combinations, and so on, but also play against computers. So that was interesting. I don't know how he felt about that idea of introducing computers to chess years later in 96 and 97 when he was playing against Deep Blue and eventually lost. So Deep Blue, developed by IBM, is not exactly AI or machine learning system in our present day understanding, but it is, a large component of it is what we would call AI in the traditional sense of the word. And what's interesting, it was developed by the team in IBM who specialized in speech processing and natural language understanding and recognition. So some of this team then further migrated and became leadership team in Rentec, in Renaissance Technologies. But some of the leaders were quite responsible for Deep Blue, and in fact, the name Deep Blue is due to a person who then served as a CEO of Renaissance Technologies for 30 years. So interesting story there with chess. Going back to what chess is all about. So suppose I show this chessboard to Garry Kasparov. He immediately knows, just by looking at this, what this position means, how we got there, what it represents, and so on. If I show it to somebody who doesn't play chess, then it probably means nothing. It will take a while to decode, understand how we got to this situation. So this is actually one of the very famous chess positions for minutes. So the point is here, of course, is that if we saw something many enough times and practiced with this, so Malcolm Gladwell popularized this as a 10,000 hours rule, that if you see or practice many enough times with something, that's how we learn, basically. And that's what makes Garry Kasparov chess grandmaster. That's why he can quickly decode this board. So why not apply the same principle to mathematical problems? So here I show you an example of what mathematically is called a knot. And I ask you a simple yes or no question. Can you tell me if this is equivalent to what's called unknot, unknotted circle, just this piece of string without any further knottedness, can be by isotopes relate this and that picture. So here, well, actually, any guess?
Probably the unknot. That's my guess.
Yes, that's correct. It is unknot. How about this one? Any votes? Who thinks it's unknot? Who thinks it's knotted?
I'll go with the unknot again, just because.
I actually don't remember. But you see the point. So as complexity increases, it really takes some training to quickly recognize and see the big picture. So we have to basically, just like on a chessboard. So when we learn combinations and all kinds of openings and closings, we basically learn big picture and try to identify important pieces of information and how it connects. So this is basically, roughly speaking, what neural nets are doing. So before I dive much further into machine learning, this is good illustration of how neural nets work. So they process a lot of data, they look at lots of examples and try to identify or highlight those important features through certain neurons. So that's basically how the process works. So therefore, if I ask a trained neural net or show it like 50 million pictures of such kind of diagrams, it can probably train really well and decide whether it's knotted or unknotted. And that's actually one of the experiments that I'm going to use as an illustration throughout this entire talk. So why is it important in topology? So far I was basically joking, very serious mathematics here. Well, here is a picture of a more knotted thing. So this is also a knot with 48 crossings. So previously I showed you knots with 10 crossings, 30 crossings, So complexity in knot theory is expressed in terms of how many crossings the smallest diagram will have. This one has 48, and it appears in a paper from about 10 years ago by these three people, Gump, Charleman, and Thompson, in the context of so-called slice ribbon conjecture. And this is a very important conjecture. It's actually, in my opinion, just as good as a smooth Poincare conjecture in dimension 4 because it tells us something deep. And what it says, or what it's asking about, is the following. A knot is called slice if you can cap it off in four-dimensional ball by a disk, topologically disk like this, by supposedly embedded in four-dimensional ball. And that's the notion of slice. And ribbon means that it's a slightly stronger condition that there is a Morse function such that here on a general disk, I have maxima, minima, and various saddles. And a ribbon means that I can do this without using maxima. So only using Morse points of Morse index 0 and 1 without Morse index 2. So a priori, this looks very similar. Obviously, ribbon is a little stronger, and famous conjecture states that these conditions are actually the same. If I can do it one way, then I can actually do it in a stronger way. So why it's interesting in topology is because community is split. We don't really know whether it's true or false. At some point later in the talk, I hopefully get to say P versus NP conjecture, and everybody believes that they're not equal. That, I mean, 90-something%, if we do a poll, we will say, no, P is not equal to NP. But here we don't know, actually. And this is a kind of, so it's conjecture. It's very interesting from that perspective, but it also taps in a world of four manifold, which is extremely rich and interesting. And that's why I meant that it's close cousin of smooth Poincare conjecture, which will appear on the next slide. So to answer such conjectures, we have to understand counterexamples or knots with 48 crossings. So this is a potential counterexample because this is a candidate of a slice knot that might not be ribbon. That's a picture taken from their paper. So if we manage to understand whether it's ribbon or not, we basically settle thing one way or the other. So, and then we have to go through this kind of examples. But pay attention that this has 48 crossings, and this is already a fairly big object. Fairly big by modern day standards that you could say, well, didn't knot theories develop all these John's polynomials and other invariants? So why wouldn't it be hard? Just throw some of this invariance on these knots. Well, the issue is that, yes, John's polynomial is well defined, but it's practically uncomputable. It's NP hard, and I'll talk about complexity later. So its computational difficulty grows very, very fast with number of crossings. So for this 48 crossing knot, it's basically uncomputable for practical purposes. Why? Because current computational techniques, computers can do something slightly above 10 crossings. Usually you can find programs which compute such invariants for 12 crossing, 14 crossing knots. But complexity of computation and the number of knots with that many crossings grows very fast, way beyond exponential. And even if you assume Moore's law, that computational power basically doubles every year, it means that, well, this grows exponentially and computational power grows exponentially. That means that on this scale, in next year, I basically move from 16 crossings to 17 crossings. In yet another year, I move from 17 to 18. And unfortunately, in my lifetime, I have no hope by traditional machines to get to the range of 48 crossings or even hundreds of crossings, which are required for smooth Poincare conjecture. So we have counterexamples, and all that's stopping us from deciding and quickly analyzing that data is complexity, really. I mean, it's not very sophisticated question, it's not very sophisticated algorithm or anything like that, it's just complexity. The traditional techniques, quantum invariants and all kinds of other invariants, are just practically uncomputable, simply because complexity grows very fast. Any questions? By the way, feel free to interrupt me at any point and ask questions. I know you've already been doing it, but I encourage more. Okay, so speaking of serious mathematics, so can computers or machine learning help us to do serious math? So this is, I guess, to many, some of the most interesting questions in low-dimensional topology to understand smooth structures in dimension 4. Why? Because in higher dimensions, the understanding of different types of spheres in different categories, so here I list topological, piecewise linear, and differentiable, have been understood quite well. And something that has homotopy type of a sphere is a sphere in topological MPL category, but well, Milner showed that in dimension 7, we famously have 28 types of smooth spheres and so on. So this is a subject that goes to late 50s. In low dimension, things are kind of simple in code, except that, well, we had to have Hamilton and Perelman to help us in Thurston in dimension 3, where the question is now settled. So Poincare conjecture is true as far as existence of sphere characterized by its homotopy type goes. But dimension 4 sits kind of in between, where there are many things we don't know about spheres, but also about lots of other things. And then that's where this slice ribbon conjecture comes in that I mentioned. And that's where yet another, probably one of the most well popularized and famous conjectures in low dimensional topology that still is unknown stands, called generalized Poincare conjecture, that every homotopy four sphere is diffeomorphic to the standard four sphere that we can define, say, by x1 square plus x2 square and so on equals. So this question, this conjecture, we don't know, like slice ribbon, whether it's true or false. So cool thing, in low dimensional topology, opinions are split, roughly 50-50. So that makes it interesting because we don't know. We probably will know sometime soon, hopefully in our lifetime. And that's exciting because we cannot anticipate the answer right now, unlike many other conjectures. So suppose we want to disprove it. Here's a cool fact, which reduces it to knot theory. So it asks for pairs of knots with the following three properties. And each property in itself is actually fairly easy. So there are lots, roughly half of the knots, which have each of the three properties. One property is that one of the knots is slice. That means, again, that knot bounds a smooth disk in a four hole. The other is not. So that means that we have to basically compute some abstraction to sliceness, and it shouldn't be zero. And another property is that these two knots have the same zero structure. If I just focus on either of these criteria, one of the three, it's very easy to find zillions and millions of examples. So what I'm asking is for intersection of the three. And once we find one, we go home disproving Poincare conjecture. Pretty cool, right? So again, it's interesting, and I don't know which way it will go, because roughly half of the knots are slice, half of the knots are not slice, and there are lots of pairs which share the same zero surgery. But exploration in this territory quickly takes us to dozens or even hundreds of crossings. So that's what I represented by the diagram. So most of the examples, there are very few knots with few crossings. There are very few simple examples. So complexity here grows very fast. So in recent years, I was involved in several projects on the subject, and they're kind of similar, and they're somewhat suitable for machine learning, and there is some parallel between them. So one question I already asked you before is showing some messy diagram like this. Can we tell if it's knotted or not? That's a yes or no decision problem. So then, so why is it good for machine learning? Because see, the configuration space of such possibilities is enormous, just like number of positions on the board of the game of Go. It's enormous. But number of moves that we need to make is very small. Here they're called Rademacher moves. So there are three basic moves, lots of possibilities to explore. This is actually a vanilla type problem for machine learning. That's where machine learning is best at. Very few moves, small move space or action space, but large state space. Analogous question, which adds one more move, called band addition, will be related to asking a question about the knot. Is it slice or ribbon? More precisely, ribbon. So it just adds one more move and gets us into the territory of this smooth Poincare conjecture in dimension 4, slice ribbon conjecture, and lots of other cool things involving involving four manifold topology. earlier today I was promising to students the first simplest example of a non-trivial slice knot. So of course, unknot a slice because you can imagine the usual two-dimensional disk bounding it. So the first non-trivial example has 6 crossings, and that's a lot. So that's the first non-trivial slice. But again, it's they all look like this because basically it means that you can imagine a band which is passing through itself, and that's part of the origin of the name ribbon. So it justifies that. There is a third version of the problem which comes from combinatorial group theory called Andrews-Curtis conjecture. So you can also phrase it as a decision problem if you represent your knot as for example, by braid, and that's an object or element in the braid group. So then basically that gets very close to formulating Andrews-Curtis conjecture that I'll show on the next slide. But here I just want to put this as a summary. These are kind of problems that with my colleagues we studied or are studying, and I'll try to report on the simplest version of this problem, but all of them share some level of similarity simply because they're basically, you go from one to another by any additional move or changing condition a little bit, but then you basically want to play the game and ask computer, can it become Garry Kasparov at recognizing whether knots are knotted or unknotted, slice or ribbon, and so on. Any questions? Okay, so what is Andrews-Curtis conjecture? It's motivated and closely related to four-manifold topology. If you think about handle decomposition and how you express fundamental group in terms of one handles and two handles without use of 3 handles, then one handles become generators, 2 handles become relations among generators. And if you're looking for something which has homotopy type of sphere, the number of generators and relations, or number of 1 handles and 2 handles, should be the same. So this leads us to a statement that we call a presentation of a trivial group. Again, think by analogy with the fundamental group of a 4-manifold built out of composition is balanced if it has the same number of relations, R1 through Rn, as generators x1 through xn. Clearly, a presentation of this form is trivial because it basically kills every single generator, so it says that the group is trivial. And the question, Andrews-Curtis conjecture, is the following, that every balanced presentation of the trivial group of this type, with same number of generators and relations, can be reduced to this one by a sequence of very specific moves. Again, think of many configurations, non-commutative type structure, but very few moves, small action space. So these are the ones which are basically multiplication by generators and various conjugations. Okay. Well, there is a generalized version which also believed to be false. I will say in the next slide that this conjecture, unlike the other ones which I mentioned, is believed to be false by experts. So even if you throw this additional relation, or if you throw them, then that's also yeah, so believed to be false. Interestingly, you can kind of start exploring this or trying to disprove by finding counterexamples with small number of generators and relations, and in small length. Unfortunately, there are no counterexamples, but there are lots and lots of potential counterexamples. For example, Agbolut and Kirby, who are topologists, and again, as I say, this conjecture is actually, it's phrased in combinatorial group theory, but it's actually rooted in topology. So they give a family labeled by integer n, and they basically say, okay, go ahead and prove to me that this can or cannot be reduced to a trivial presentation. So here there are 2 generators, 2 relations. Doesn't look too big, right? But nobody knows how to deal with it if n is sufficiently larger than 5. On the next slide, I'll give you a theorem that settles it. So this was an 85, but there is a theorem settling it for n equals 5. Right, so it also has a connection to another important aspect of low-dimensional topology called property R, which basically says that S1 cross S2, product of circle and a 2-sphere, is the only 3-manifold, the only manifold that is a characterization of zero surgery on unknot, and that's true. So David Gabay proved that. In fact, he demonstrated analogous properties for other simple knots, but then it led to whole line of work generalizing this conjecture in many ways. Many of the generalizations were proved, many disproved, and this is one of those which again has important consequences, but I guess I won't go into much detail. This is actually from the same paper of Von Schormel and Thompson, which I showed earlier, which has this 48 crossing counterexample to Sans-Rippen conjecture. Right, so this is analogy or something that I already said in words. If you think about generators in relations as one handles and two handles, then that's the origin of this Andrews-Curtis conjecture. Then having potential counterexample to Andrews-Curtis automatically gives potential counterexample to smooth-Poincare conjecture. So they're connected. And that's the theorem by Gomf 6 years later, after this family was proposed by Agbulut and Kirby, where he settled this in the case of SPC4, show that this is standard. Okay, so this looks kind of easy, but there is an interesting notion here of hard cases, and this is something I learned only after doing this machine learning and then going backwards, actually revisiting what in trying to interpret results. So it's an interesting situation where many examples will turn out to be easy, at least for somebody as trained as Gary Kasparov in the world of knots or sliceness and so on, but there will be always some set which is really hard. So some particular knots, or in this case, presentations of trivial group, which are actually hard. So there is an interesting theorem from a few years ago, that's not too long, it's 2015, which says that if you take just this presentation, you can show that it's a trivial group, but there is a theorem saying that you cannot do it in less than 10 to the 10,000 moves. So, and of course, in every practical implementation, that's going to be something to look for. It's going to be hard to find. Anyway, so this is just to show you kind of problems that we try to approach, or mathematical problems that we're interested in. So they're all very similar. One is very simple, deciding whether a given presentation of a knotted diagram is actually representing unknot or not. And that's the one I'm going to focus on the rest of the talk. But I want to show that it's a really close cousin of several other problems. Aside from AC, this Andrews-Curtis conjecture, we actually don't know the status of this other very important conjectures in topology, and that's where the series mathematics comes in. So, any questions about this one? Yeah, feel free to ask, don't be shy. Okay. There is a good reason I showed Terry Vinograd and his work and students in one of the first slides. So way before machine learning was picking up and used, from the viewpoint of natural language processing and natural language understanding, he already back then, before computers were strong enough to do it, he said he tried to invent really important examples, which these days are called Vinograd schemas, of sentences which would be hard for a machine to understand, or it could be used as a benchmark, as a stress test. So suppose we want to understand the sentence or translate it into a different language. So then here is an example. So the trophy would not fit in Brown's suitcase because it was too big. If I ask you what was too big, trophy or suitcase, from the context of the sentence, we immediately know that trophy was too big. That's why I didn't fit. But machine basically has to learn this. It has to understand it. And if you're translating it into a different language, it could make huge difference, because there will be genders and all kinds of connections between sentences that will be totally messed up, and eventually things will totally break unless we really understand what's going on. So he was very good at coming with this stress test. So examples, again, called Vinograd schemas. Here is another metric.
What's the second example there? Sorry.
Yeah, so the town councilors refused to give the demonstrators a permit because they feared violence. So who feared violence? Again, we understand, but your machine understands. So here is another metric how people in this field in computer science related to language processing measure quality of understanding or translation. This is the vertical axis is so-called BLUE score. This is bilingual evaluation understudy, and score above 20 is where the systems hovered back more than 5 years ago. 30 is what normal human translator can actually do. 40 is really good, and so on. So that just to give you an idea. So this was doing poorly.
What does MT stand for?
MT, machine translation. So I'm going to go through all, well, not 3 of these, but 2 of these. So the history of the subject is the following. So again, Terry Vinograd is the founding father. So he was starting to think about this back in 70s, and it actually took off quite well in 90s when, of course, computers were developing fast. So that's when IBM's team focusing on machine speech translation and understanding developed Deep Blue. Actually, the reason they developed Deep Blue is because they wanted to advertise their work, because they were tired sitting in offices and using all this cool stuff, and they basically said, hey, we have to raise awareness and money, so let's do something cool. And they came up with a game of chess. They thought that understanding the game of chess or chessboard is very much similar to understanding the language. And then again, hopefully this talk will convince you that that's the case. So MT stands for machine translation, and in the 90s and early 2000s, the way it worked was basically statistical. So it was Bayesian optimization type translation, which consisted typical SMT, statistical machine translation, had 2 components. One was so-called language model. So the goal of that was to understand the meaning of the sentence. And the other was translation model that was to generate from the meaning vector to generate the sentence in the other language. So it was basically broken in 2 pieces. And one can write formulae in terms of probabilities, how one does conditional extremization, optimization there, and so on and so forth. So I'm not going to talk about this red versus blue lines. They're kind of similar, but what you see here is that neural machine translation overtakes these 2, and then again, SMT is basically past history around 2015. So lots of things will happen around that time. So again, pay attention to some of the time. So here is how first neural machine translation worked in early days, maybe around 2015, 2016. It also consists of 2 components. One is analog of translation model, the other is analog of language model. And typical neural net architecture that would do it would be called sequence to sequence. It also consists again of encoder and decoder. These are analogs of this. And it does pretty much the same. So it's a bunch of basic components, typically recurrent neural nets, which take pieces of the text one by one, say sentence by sentence or phrase by phrase or word by word, and try to convert it into some vector in very high dimensional space, which roughly encodes the meaning of it. It passes it to a language model, which would generate from past experiences and seeing lots of text, the best suitable candidate in another language. So that's typical architecture that was used back in 2015, 2016. As you can see, it's not perfect. So those of you who speak German probably already have been laughing at this for a while. So the English sentence that goes in is, you asked us to call you back after last Friday. The German translation, ich hoffe jedoch, dass Sie bei Ihrer Reiseplanung weiterhelfen. So the German sentence has no Friday, and its meaning is quite different. It mentions travel plans and it's actually not terribly far. Again, those who speak can probably see how it happened, but it's a different sentence. The meaning changed. And if you want to apply this to topology where details matter, that's certainly not going to fly. But even in translation, it's very important because we don't want small misunderstandings. They can be extremely offensive sometimes, and we don't want this to happen. So it is important to have very high standards. So we need what in statistical translation would be called context vectors. So part of the problem is that doing it this way, what happens is that this RNNs, when they're applied, recurrent neural nets, when they're applied in this sequence, they quickly forget meaning over a long distance. That's one part of the issue. Another part of the issue which existed from this machine learning point of view is that there are functions called activation functions that are being superimposed one after another. So we get convolution of several of them, and they'll typically look like, there are some examples like sigmoid functions and so on. And once you superimpose them many enough times, you get vanishing gradients. And all neural nets usually work on some kind of optimization where they try to have some version of gradient descent. So once you superimpose this activation function many enough times, it's really hard to get meaningful gradients out of it. So that's another part of the issue, and there are many more. So yeah, these are some funny examples of translation in other languages, which again, if you speak, you can probably relate or see. But the solution to this came a couple of years after. So that's where things started developing really fast. So basically in 2016, another mechanism called attention mechanism came to the scene, and it basically was providing this context vector. So the idea was that in parallel with the entire process, there would be some other part of the neural net keeping track of the meanings and relating different things. So this was much more global way of keeping the data and information. I'm not going to go in detail. I just illustrate this, for example, by this what's called attention metrics. In this case, when you have it's self-attention, it's comparing not two different things, but rather different. It's comparing relations between parts of the same sentence, for example, in this context. And again, that's a kind of sentence that where this is non-trivial or important. For example, if I ask you in the sentence, the animal didn't cross the street because it was too tired, who was tired, the animal or the street? And what does it refer to? You probably can quickly answer, right? But for a machine, again, this needs to be learned from context, and this metrics basically keeps track of this context. For instance, here in this matrix, the neuron between animal and it is more activated, although you can also see connection to street and so on. Okay? So that's what attention roughly is. And then the team at Google basically suggested that let's throw everything away and focus on this piece of machine, of the component. It still had lots of bells and whistles, but basically that's what they proposed, and that's the title of their paper. They say attention is all you need. And this architecture, again, it has lots of bells and whistles, and illustration is on the right, but it doesn't matter what it is. Actually, suddenly performed really well and was extremely good on all kinds of tasks. So here it describes, for example, that it quickly raised the blue score that I was showing you in 2015, 2016 was hovering at the just a little bit slightly above 20. It went to almost 42, and then again, it kept growing. So this did really well in a very short period of time. So this is an example from machine learning point of view of a very cool, successful architecture that's used nowadays, and this is what's called transformer. So I don't know if the name is here. Oh, yeah, well, at least it's here, but I'm not sure. Yeah, here it is. The architecture called transformer. So these are, again, Vinograd schemas. They're these fun examples of sentences that have to be translated, in this case, into French, which is quite sensitive to gender and other things. And the cow ate the hay because it was delicious. Again, who was delicious, cow or the hay? So that has to be understood. And Transformer obviously did much better than Google Translate, which used seek-to-seek. That was back in 2017. And by the way, I encourage you to, if you want to learn more, listen to various talks or read papers by Lukasz Kaiser, who was on this DeepMind paper from Google. Here's another example. So in particular, Lukasz Kaiser would explain that this architecture transformer, it's one of the coolest in machine learning. It's maybe like, I don't know, luxury car compared to Honda Civic, which was the seek-to-seek or feed-forward neural net. It can do a lot of things and very powerful. So in particular here, he says that, well, if you give it just one word and ask to generate an article, say for Wikipedia, so it does extremely well. So the word is transformer, and just from one word, it writes the entire article. Here in this version, it imagines that transformer is a band and goes through, it contains such and such members, some Japanese band, and it goes through typical history of music band that dissolves and then has some drama and so on. So it actually looks like a real article. So it is actually really good on all kinds of tasks, even though it was designed for completely different things. Anyway, the history doesn't stop there. So when we're working on this unknotting project, trying to see how well machines can learn whether something is knotted or unknotted, another thing came out in 2020, just before when we were ready to finish the paper. A new architecture was proposed, also in part coming from Google. And this, by the way, is son of Alexei Kitaev, for those of you who know Alexei Kitaev. That's again Lukash Kaiser, and they proposed yet another improvement of transformer, now called reformer. So this is definitely like Lexus of machine learning architectures, and it does extremely well. But again, I won't even go there. So, well, I gave you a tour through very powerful machine learning techniques and history in this very condensed period of time, starting roughly in 2016, going to 2020. So hopefully it gives you an idea why things are happening now, what is happening, and so on. And we decided to apply all this cool architectures to the simple problem of deciding whether this is knotted or unknotted. Well, this thing can be easily represented, as I already mentioned, as a word in the braid group. And the very fact that we say word in the braid group already should ring a bell that, oh, if you want to understand the meaning of the word, or does it represent knot or unknot, natural language processing, natural language understanding should be perfect for it. We can just apply all this to it. After all we want to know is to give a word in a braid group that represents this mess and ask, is it knot or unknot? So that's what we're going to do.
If you go back, you have, no, go forward. You have 3 people and 4 names.
Yes, yes, I'm not, you already have my picture in front of you. So these are pictures of collaborators on that paper,
Okay.
which came out in also 2020.
Okay.
So it was shortly after, as you can see, this is from early 2020, and it delayed our paper because we decided, okay, something cool came out, we should explore it, and we did experiments on all these different architectures and neural nets. And what we found is that it doesn't matter which one you use. So we found several surprises. One was that we used feed-forward neural net, and that's like Honda Civic in the world of machine learning, AI. And then we used some of these more sophisticated ones, and they all gave good results, in the sense that they learn very fast, and they learn really well. Another thing we noticed is that if you actually go to more complicated knots, increasing number of crossings, or here a braid length is analog of number of crossings, things perform actually better. So in the paper, we discuss why this happens, especially for the late phenomenon, I mean for the second phenomenon, that increasing number of crossings improves performance. We think that, at least in part, it's very much like playing chess against stronger opponent or seeing more complicated cases. It's like when we go to gym and try to push ourselves to the limit, it makes us stronger. And that's we believe is part of the deal here. But otherwise, what we learn from Bert's point of view is that it seems like this knotting problem is actually a very simple problem, because it didn't matter which architecture we use, and it does so well, quickly going to 100% for hundreds of crossings. And by the way, again, or what we need for topology is hundreds of crossings. That's important.
How do you certify correctness here?
Well, the way it's usually done is that you train your neural net on, first of all, you have to have a lot of data. And we generate lots of examples, which are diagrams looking like this, which we know are knots or unknots. So we basically, to generate, for example, such unknots, what you can do is to start with unknot and start doing random Rademacher moves, scrambling it and making it like such a mess. It's the same with other knots. So we have to, there is a long story, and there are several sections in the paper, how we prepare this data set, because in computer science, it's very important that you actually eliminate all kinds of biases, because you could be constructing it in a simple way, and then if machine learning is basically learning how you construct it, it's not really solving anything. So anyway, you have to have lots of data sets generated in different ways, and then typical thing is you split it 80-20 or something like that. You train on 80% of noted and unnoted example and use the rest to test. So that's what this graph represents, how well it actually learned.
And this algorithm only gives the answer, or it also provides some algorithm for unnoting?
Very good question. So this is a decision problem. It's yes or no. So the goal of this was, reformer, yes. Its goal was to learn and tell us yes or no. Later on, in a couple of minutes, I'll show you different architectures which actually play the game. So their goal is to do the moves. And of course, if they certify that, oh, they found the sequence of moves, we can ask, okay, show us, and we can check. Yeah, so that would be actually more serious and more. Any other question? Yeah.
Is it a separate model for each braid length, or can you like train the model once and then run it on various braid lengths?
Yeah, that's another very good question. What we want, of course, is that this is sometimes called transfer learning. So we want to make sure that it learns and we can vary, at least within fairly broad range, number of crossings or lengths. So typically what we did, we tried to make sure that it works really well within range from, I don't know, 15 to 100, something like that. And that was part of the goal. And that was, again, very successful. There are some techniques which are clever, which given on top of it, architecture add various bells and whistles which help machine to do this transfer learning. Surprisingly, we didn't have to use them, even though we were aware of it. We tried, but it didn't affect performance. It was already fantastic, just surprisingly from get-go. So it sounded like this is really easy problem for. So I want to dig into this for a couple of minutes before I show you the reinforcement learning results and conclude. So this question, whether it's an easy problem or not, actually has been looked at. So the complexity is usually measured in existence of algorithm of whether it's a polynomial time or it could be non-deterministic polynomial time, which means it's like a Sudoku puzzle that if you provide a certificate that may be quickly checkable, but finding a solution may be hard. So it was shown in 2008 that the unknotting problem in one direction is in complexity class NP. So that means that if you provide a certificate, it can be quickly checked, but finding it may be hard. So in the opposite direction, knotedness problem was also shown to be in NP. So here, Greg Kuperberg did it using generalized Riemann hypothesis, which is something that's not been proved, but this conjecture or this additional assumption was relaxed shortly after. And what this means is that the problem that we're trying to decide, yes or no decision problem, whether this messy diagram is knotted or unknotted, is mathematically rigorously proven to be an intersection of complexity classes NP and what's called co-NP. So when negations are also easy to check, that puts it in complexity class co-NP. That's one of the classes. And what's interesting about it is that many problems that started life in intersection of NP and co-NP eventually were found to be polynomial type problems. So it justifies that these are relatively easy. For example, whether an integer is composite or prime is obviously in complexity class NP. It's less obvious in complexity class co-NP, and eventually polynomial time algorithm was found. But it's not known, for example, for problem deciding whether integer is a product of two primes, specifically two primes. So we don't know how complexity classes are arranged. As I mentioned before, of course, there is P versus NP conjecture here. I'm showing the Venn diagram how these complexity classes overlap, assuming that P is not equal to NP, and according to many other beliefs, people also don't know, or we don't know, whether NP, for example, coincides with co-NP. So here I'm showing the version which assumes that they don't. But anyway, this is probably what most people would consider reasonable or agree on. And this kind of justifies that our problem that we're trying to solve is very close to P. So maybe actually secretly, we don't know mathematically the algorithm, but maybe that's what machine is finding. It's basically getting very close to polynomial time algorithm, and that's why it's just doing so well. So Mark-Huckenby reproved the Stock statement that knotting problem is in coin P, or equivalently reverse knottedness is in P, without any assumptions of generalized Riemann hypothesis that Greg Kuperberg used. But we shouldn't celebrate too early. So this previous result suggests that it's easy. But then what's interesting is that if you try to ask whether you can do it with, for example, imposing a bound on number of steps that you use, then it quickly becomes NP hard. So this is an interesting problem, which is kind of on the boundary. It's again teasing us. So it's there are some indications that it should be easy, some indications that it should be hard. And since I'm talking about complexity here, I mentioned one of the papers also from Greg that certain things, and this is very typical, illustrating that any kind of invariants that we construct on quantum topologies, that we construct on quantum topology, are basically uncomputable. So here are the complexity classes for simultaneously sharp P complete. So this is class way harder than in the Venn diagram I was showing before with this NP. So anyway, this is basically to say that things like John's polynomial are hard to calculate. So now to approach my conclusion, I'll show another kind of game that we played. So here we ask machine not just to predict whether a given diagram is knotted or unknotted, but actually play the game. And we will show that lots of diagrams and ask to play the game basically itself, and show us the sequence of moves, which if successful, lead us to unknown. So this is yet another part of machine learning, in this case, reinforcement learning. And there are different architectures that we explored. So again, like the previous decision problem, we tried many different things. And our W here stands for random walker. So in machine learning, the baseline of the first obvious thing you do is just start doing things at random. Of course, that usually doesn't lead anywhere. So not surprisingly, as the complexity increases, the chances of doing anything is just go to zero. So that's why this quickly goes to zero by 100 crossing. Sometimes it succeeds, which actually is interesting. So then there is a fairly traditional architecture called A3C in reinforcement learning, which is very inexpensive in terms of resources. And here it performed moderately well. So it was better than random walker, but it's also going down as we have more crossings. So it's learning, but it's struggling. And then there was one which was extremely successful. So again, it showed same interesting feature that you increase complexity, increase number of crossings, and it actually does to some extent even better. This is called TRPO, the blue dots, and this is trust region policy optimization. So what it is, it's the following. So typical machine learning algorithms and architectures are based on various versions of gradient descent or optimization. So the problem is that if your landscape is very rigged, like on this picture, well, you can make a step in a kind of, which seems right direction, right where you're standing, but if landscape is of this type, you can make a fall and never recover. So trust region policy optimization is an algorithm that basically prevents this problem. So what it does, it says, okay, where you're standing, it explores the region around it, and makes most optimized decision within that region. So then it makes next move. So it's very slow compared to usual versions of gradient descent, and it takes a lot more resources. And this is a caricature actually of what it really does, but it's much more careful and successful, and that's why I guess in this case it's learning really well. So here is another plot, basically trying the same thing, playing the game. I show it some complicated diagram with lots of crossings and asking, can you show me, play the game whether it's not or unknot? And what's interesting is that the number of moves, so this is average number of steps that it does for these different diagrams. For this blue guy, they don't grow very fast. So they remain quite reasonable. So it's actually definitely learning and finding probably one of the most optimal paths, at least on average, to the unknown and completely trivial diagram of the unknown. So hopefully this hour illustrated that why I believe machine learning can be successful for serious mathematics. So this last part about reinforcement learning is good illustration that if it finds something, it really finds it. So then we can basically put on a paper theorem that a knot with 48 crossings is slice or ribbon. So just because it found a way. And we as human, unfortunately, cannot handle this level of complexity. Invariants that we're trying to construct from fancy knot homology or quantum invariants are just hard. I mean, they're way outside the area where we need to compute them. So this is, I guess, the main message I want to give you.
So thank you very much. That's very interesting. Also, questions?
What if you tried to teach a machine learning algorithm to solve an undecidable problem? What would go wrong?
I don't know. Actually,